In this lecture, we'll discuss merge sorting. At the end of this lecture, please make certain that you're able to explain the merge sort algorithm and its runtime, including the divide phase, the conquer phase, the runtimes for both of these phases, and given in elements, show how the algorithm works. The merge sort algorithm is an example of a divide and conquer algorithm. In divide and conquer algorithms, we have 3 steps. Step 1, we divide the problem P into 2 smaller problems, P1 and P2. Step 2, we conquer each subproblem, solving it recursively. So we keep breaking it into smaller and smaller subproblems. And then step 3, we combine this solution for these subproblems into a solution for the main problem. So for merge sort, the problem that we're going to solve is that we have an array that needs to be sorted. The merge sort algorithm divides the array in half. We'll keep dividing it in half and in half and in half, and recursively sorting each subarray. And then we'll combine these sorted subarrays to yield the complete sorted array. Using the abstraction that this is an array, we cut it in half. On the left we have half, on the right we have half. We keep cutting the array in half until we get down to 1 element. And then what happens? We're going to merge these 2 elements together into a sorted list, these 2 together into a sorted list, and keep traversing back up and up, piecing them all together. On the next slide, I'll show you a demo with numbers. Assume this is our array. It's unsorted and it has 8 elements in it. The way merge sort will work is we're going to divide the array in half. So we'll take this half and then this half and keep dividing it in half until we reach 1 element. Now we've done the divide step. We took half of the array and we keep cutting it in half and in half until we get to 1 element. Half, half, half until we get to 1 element. Now we have to do the conquer stage. The conquer stage, we're going to merge together the 2 arrays at the lowest level, pass it up to the higher level, keep passing it up, and put together a sorted array. So let's merge together 9 and 2 in sorted order. And we've done this before in our class where we've taken 2 lists and determined how to merge these together. You were given questions on your homework assignment for this. So merge 9 and 2 together, we end up with the array 2 and 9 in sorted order. We'll do the same thing here. So now we're going back up. This is a recursive algorithm. So we kept cutting in half. Now we're returning. Merge together 23 and 14. Well, 14 comes before 23, and then we have 23. Okay? We're going back up. Okay? What happens next? We've got our 2 lists, 2 and 9 and 14 and 23. We merge these together. What do? We compare 2 and 14. 2's less than 14. So 2's going to go first in our array. And imagine we have pointers here. Okay? So we've advanced our pointer. We're looking at the next element and the array on the left, but this element at the array on the right. 9 and 14. 9 is less than 14, so 9 is going to go next. Where's my color? And we're done with this array, so our pointer is going to move over, and then we just go ahead and put in 14 and 23. Used the wrong color there. Okay. The same thing is done on this side. Okay, merge 19 and 1 together. We get 1 and 19. Merge 8 and 12 together. We get 8 and 12. And this is going back up. Okay, this is as we go back up. Now we've got 2 arrays, 1, 19, and 8 and 12. We merge these 2 together, passing it back up, yielding the sorted array 1, 8, 12, and 19. Now we have these two arrays, and we'll merge these two together, passing it back up, and that will be our finished product. We have our sorted array, and we're done. Now we need to discuss the runtime. Let's discuss the runtime for this classic merge sort algorithm. Let's first talk about the merge operation. Okay. On every level here, once we've cut the array in half, we merge together. Okay, we'll merge together arrays 9 and 2. So we examined each element in the array and pieced it together. So that's one look, two looks. Then we did the same thing here. So we examined every element, piece it together. Thus, we did this, and what would the runtime be? We looked at all 8 elements. Okay, so at each level that we're coming down this array and we're going to do the merge at each level, the merge takes, you got it, linear runtime. Okay. And then how many times do we do this? How many times do we cut the array in half? How much time does that take? Okay, determining the midpoint, that's just a simple function. Okay. That's just constant time. But how many times do we do this? Okay. How many times do we cut the array in half and then merge it together and pass it back up? N is 8 here. How many times did we do it? 1, 2, 3. What's another way to write 8? 8's the same thing as 2 cubed. Now if we take the log of 2 cubed, base 2, what do we get? 3. If you'll notice, this is the height of our tree. So how many times do we cut the array in half and then merge it together? We do this log n times. But at each level, the merge takes linear time, so our runtime is going to be, for the entire runtime, is big O of n log n. Let's examine the code for the classic merge sort algorithm. This is the driver. The driver takes a parameter, our array that we're going to sort. It creates a new temporary array that will hold intermediate results. Is this an in-place algorithm? We create a temporary array that holds intermediate results. So no, this is not an in-place algorithm. We have a temporary array that's created. Okay, so the driver will call merge sort down here, passing in the original array A, the temporary array that's going to hold our results, and then the range of the array that we're sorting. So from 0 to its size -1, which will give us all of the elements. Now, merge sort is invoked again with the original array, the temporary array, and then the left and the right. It's a recursive algorithm that's going to keep cutting in half our array. Here we check to make sure that we have more than one element. We're going to keep cutting the array and then subarray and subarray, etc. in half. We'll invoke merge sort again, okay, on each half of the array, the left half and then the right half, and we'll do the merge operation. So this is pretty simple code when we look at it. Okay, the merge function just combines the two arrays together in a sorted order. And you've given code already that will do that with the merged list. The next question I have is this algorithm a stable algorithm? That is, do equivalent objects retain their relative positioning after they're sorted? Well, the answer lies in the code right here, okay? It lets the left, if the left is less than or equal to the right element, the left element gets moved first into the temporary array. And that's done throughout. So yes, this is indeed a stable algorithm. Okay. Again, it is not an in-place algorithm, not in place, because we use an auxiliary data function to hold our intermediate results. Let's discuss more about the runtime analysis of our merge-sort algorithm. What is the best case, do you think, for this? Best case runtime. That is, let's think of scenarios. Okay, we have three potential scenarios. We have the array is already sorted. We have the array is in descending order, and we want it to be in ascending order. And the array has objects that are just randomized. Array with random objects. Okay. Is there any difference if the array is already sorted, okay, in our runtime? Okay, if our array is already sorted, are we still going to divide our array in half until we get down to one element and then piece it back together? Yes, so our runtime here is still big O of n log n. Okay, no difference here. If our array is in descending order, do we still keep cutting the array in half till we get to one element and then merge the arrays back together? Yes. Okay, so our runtime here is big O of log n log n. What about if we just have the random objects like we did the demo with? Again, we keep cutting the array in half and then merging it together. If we cut the array in half, we do this log n times. The merge operation is linear, so n times log n is, again, big O n log n. Okay. So irrespective of how our data is used with the merge sort algorithm, okay, our runtime is always going to be n log n. Okay. In summary, is it stable? Is our algorithm stable? Okay. Stable, yes, it is stable. And is it in place? Okay. No, it's not in place. So we typically don't like algorithms that aren't in place because that requires extra space. Okay. If we have 1 million objects or 1 billion objects in our array and we want to sort it, what have we just done if it's not in place? We created that temporary array for merge sort, so we've doubled the space that's required. Because it's not in place, we're going to look at another algorithm called the quicksort algorithm that is in place, but maybe its runtime isn't always guaranteed. So that's our next lecture. Thanks.